Hello, I'm Brian Smith. I'm the Aquifer Science Team Leader at the Barton Springs Edwards Aquifer Conservation District, and I'll be talking to you today about some of our studies for enhanced recharge to the Barton Springs segment of the Edwards Aquifer, and I'll also be talking some about some innovative tools we're using to study the Edwards and Trinity aquifers, mainly multiport wells. And I'll show how those are combined in our studies of the Antioch Cave, where we're actually inducing recharge into the Edwards Aquifer. Okay, so the title of my talk here is Recharge Enhancement and Multiport Well Monitoring at the Barton Springs segment of the Edwards Aquifer. And you notice down below I have Brian Hunt listed. He's done work with us for 20 years at the Barton Springs District and very instrumental in a lot of the studies that we have been doing. And on the screen here is from Onion Creek, and looking at this facility that we built and some recharge pipes that help direct water into the cave. And so that's what I'll be talking about largely in this segment. Okay, just sort of a map of the area we're dealing with. So if you look in the upper right of this figure, city of Austin, really much of this is city of Austin, but that's downtown Austin, the Colorado River. And you can see Barton Springs here I'm pointing to. And so much of this part of the Edwards Aquifer feeds into Barton Springs as the main discharge point. Of course, once we get closer south toward the Blanco River, then much of that water goes down to San Marcos Springs. But we've also found from our studies that water can move in a lot of strange ways, depending on heads and rainfall and drought conditions. But today I'll be focusing on Antioch Cave, just here west of Butte, sitting on Onion Creek. And you can notice this is on the eastern side of the recharge zone for the Edwards, just before it goes on to the confined portion. So this is the last opportunity for water flowing in Onion Creek to recharge into the Edwards Aquifer. Hey, here's just a nice view of Onion Creek, the way we see it most of the time, unfortunately without water in it. But most of the recharge occurs along creeks from the contributing zone as they cross the recharge zone. So that means that water falling on rocks that are basically Trinity, and what doesn't recharge or evaporate runs off into these creeks, crosses the Edwards recharge zone, and some portion of that then actually recharges the Edwards Aquifer. And that recharge is done through numerous caves and fractures that are in the creek beds that help introduce water into the aquifer. And we also have water in the upland areas that also is very significant in recharging the Edwards Aquifer. And you notice there's a grate here it's actually over a cave. It's called Cripple Crawfish Cave. And so under wet times, water would recharge into that cave. And this is on City of Austin properties for watershed protection. So they've been excavating that cave to allow more water to recharge that's flowing along the creek here. And this little inset shows under wet times, and that same cave entrance before a grate was placed on there, nice whirlpool as water is making its way into the aquifer. So here's a schematic sort of showing how this functions, very typical of any karst setting. But we have upland areas. Say here's a sinkhole, and during rainfall events, runoff, localized runoff will go into the sinkholes and find pathways down to the aquifer. But we also have along creeks, we have some of these recharge features. And since there's water flowing in the creeks more often in these upland areas, then this is where we get the majority of our recharge to the Edwards Aquifer. And so this shows, we have monitoring wells, and the colors indicate dye traces that we've done as we put dye into some of these upland sinkholes and chased it in with water from water trucks or fire hoses. And then when we have water flowing in the creeks over the recharge features, we'll inject dye and watch as it makes its way ultimately to Barton Springs. Or at least most of that water that we're dealing with is flowing to Barton Springs. And the well is also illustrating how we sometimes pick up this dye moving through the aquifer. In many karst settings, you think, well, you're not likely to really tap into one of the conduits where the dye could be moving. But this particular aquifer, the Edwards Aquifer, is a lot of diffuse and intermediate flow and conduit flow. So water flowing in the conduits might also flow back into the matrix. So we actually do see dye moving through the aquifer from a number of our dye traces. So here's just a figure showing this is Flint Ridge Cave, not far from the new Highway 45, and showing after a nice rain event, water flowing into this cave. So here's recharge in action with a couple of geologists kind of having fun playing in the rain. And getting back to that other figure that I showed, well, this is a different view, a different picture of that same cave, Crippled Crawfish Cave on Onion Creek, with a nice whirlpool going into it. And here we have, this is Antioch Cave. So this is what I'll be talking about mainly. And again, before any engineering work was done, there's just this little crack in the bottom of the creek bed and a whirlpool going in. But one thing that's kind of sad to think about the history of this cave is that somebody got a little too curious about this water going underground and got a little too close and got sucked in there. But that's what brought this cave to the attention of the groundwater district and other people. Certainly the locals, the ranchers, and whoever lived nearby knew about this cave, but this got in the news, and this brought the Barton Springs district interest into acquiring this property and doing something to help augment flow going into the cave. So that's what I'll be talking about here. Here under drier times, showing this little slot. It's probably only about 1.5 feet wide with a nice boulder stuck in there. So at times this thing would clog up and water would not recharge at all. And other times it might, some of this debris and rocks might get flushed out and allowing for more water. But the district saw the possibility of enhancing recharge while at the same time eliminating storm flow. So we don't get all the sediment and contaminants associated with storm flow by the system that was developed for Antioch Cave. So here, if we look now, this is just a cross-section, schematic cross-section showing, so here's the channel, main channel of Onion Creek, and here's the cave. And so this concrete vault was built over there with initially with one valve, but also a hole to put in another valve. So you see the cave goes down, it goes down a shaft for about 40 feet. And then from there, there's lateral crawlways. A couple neat pictures to show here in a minute. But you can see from the scale, 20 feet here. It's not a very big system at all, but it actually does take a good bit of flow, which I'll talk about that shortly. So here's looking up from the bottom as the cavers rappelling down from up above. And here we have a caver. This is Peter Sprouse, as our environmental, who's crawling through there. So this is where, when it's wet times, this huge amount of water is flowing through. So this kind of narrow crawlway actually takes a lot of water and directs it by one pathway or another into the aquifer. We can't get too far down there. We're not skinny enough to really follow the pathways that the water goes, but it's a good illustration of how water is moving through a portion of the vadose zone. So getting back again, here's the cave again with flow going in. So if you imagine, that water is just making its way through pathways to the aquifer and ultimately to Barton Springs. And we've done some dye traces showing how that moves there, interacts with some of the wells along the way, and ultimately discharges at Barton Springs. With a distance of about 12 miles, it might take, depending on the flow conditions, it could take 4 or 5 days, or maybe even a couple of weeks to travel that pathway to the springs. So here we are under kind of dry times. This is the vault as it was built back in the mid-90s. The guy facing the camera is the engineer that actually designed this. So when we brought him back out of retirement to work on augmenting this and upgrading it to a more automated system, he looked at the box and was surprised that it was still there. After all the floods that have been through here, he built a really strong box. And on one side, you can see where there's a hole that's plugged up, but it's a hole for another valve. So our goal was to take, instead of having one valve on one side, to have 2 valves letting water go in and have those controlled so that under storm events, when the water is contaminated, we close the valves, not let that water go in. Then they would open up later to let fresh, better quality water recharge the aquifer. So anyway, let's step back and think a little bit about what is the purpose of this system, the BMP, best management practices. But in the water engineering world, that's what we call these kind of systems. But first, we wanted to improve the quality of water entering the cave by preventing the storm water that's full of sediment and other contaminants, prevent that from getting into the aquifer. We want to increase flow into the cave, which is basically by not letting it clog up like it would in the past. And this could ultimately provide more spring flow during periods of drought. And it's not just that this water all goes right to the springs because of the nature of the system. It does, some of this actually goes into storage so that as we get into periods of drought, we'll have more water in storage that can then feed into the springs. Okay, so here we're looking at, as we were having another valve installed, and you can see this pipe that's been put in here and a screen. So this is like a large screen to keep out some of the debris that flows in the creek while letting water go in. We're lucky that we had the drought to do this, although when we had a grant to do some of these studies, and at the time when we were supposed to be sampling, it was dry. So we had to get an extension on our grant, which was understandable, and we got that easily. And finally, we got some flow going, which I'll talk about here shortly. So we also widened the opening a little bit, not so much to let more water in, so we think the restrictions are further back in the cave, but just to get more safer access for people to get in here to do some studies. And here's the, to the right is the original valve that was installed in the mid-90s. And this has continued to be manually operated. That is opened up with an air pressure tank to open and close this butterfly valve as needed. But the blue one on the left is the new valve. These are like 36-inch diameter valves, so they allow for a lot of water to pass through there. This too is operated with air, but we have a system that measures the turbidity of the water flowing by. And when that turbidity goes up, the valve automatically closes. When the turbidity gets low to certain preset points, the valve will open again and let the better water quality go into the system. So here we see it as it was completed, and maybe a little bit of flow going on there. Most of this water is just pooled up, but we see this long segment of pipe, or about 15 feet of pipe, that's just solid pipe. And we did that so we could put a flow meter in there to record the amount of water flowing into the system. So we'd also have this other valve. If it's open, we can only estimate that flow, but we might open it or closing it depending on the circumstances. Then we have some 30 feet of pipe that's basically a screen to let water in and keep the debris out. And then you can see this other concrete system going up the hill that goes to all of our instruments that are up above the floodplain. And just a view from, say, Google Earth, aerial view, we see on the top here, this little red square shows about where the BMP is. To the south is Syntax Quarry operations. And again, this is just a little bit, about a mile west of the downtown Buda. And in the lower section, we can actually see the system we put in with the vault. Here, a little brown box, and then this pipe and screen sticking out from there. And up high near the road is our little shed with our equipment, our telemetry and water monitoring equipment. So as we look at this, I'm going to think about management of the Antioch BMP. So we need to think about, as I mentioned, how this system would close during storm periods and open when the water is a little better quality. But we've had some times when this system was open while there's still some poor water quality going by. Basically, it means it's all this debris. So this is the system's actually acting as a big wet vac, sucking in everything it can. And so during the storm flow, we have a lot of debris going down there. So in this case, it actually sucked a lot of leaves and sticks and sediment to the side that we then have to clean off later. But for the most part, and if it's operating properly, the water, by the time the valve opens, then the water quality is pretty good, and there's not near as much debris that would then get sucked onto the screen. But either case, this still allows for a lot of recharge to take place. And this is just some little hydrographs that we did looking at flow going into the cave. So there's I believe it's LCRA has a gauge just downstream from the cave. And so we were looking at that, showing flow in CFS. So we had the valve was open, and let certain, a certain amount of water was going into in there and a certain amount was going downstream. So we closed the valve, say at 10:45 with a flow of 44 CFS at the gauge downstream. And then we noticed that after a little bit of time, this is going through, actually just a few minutes of time here, we saw that the flow increased. So this was showing about 46 CFS of flow that was being diverted into the cave at that time. Then when we opened the valve again, we saw it drop back down. So this was a good demonstration of at least one measure of flow going into the cave. Some of the other measurements we've taken through that pipe that I mentioned showed that we can take probably up to 100 CFS cubic feet per second of flow into this cave system. And that's actually a lot of flow when you think about long-term average discharge from Barton Springs is about 60 CFS. So under wet times, you can get a lot of water going in, or even during drought with periodic rain events, we can be recharging, providing some significant recharge to the Barton Springs segment. So here we are up on the hill looking at some of our telemetry equipment when our vehicle's down below and looking further down into the bed of Onion Creek. So with some of this equipment we installed, it's a continuous water quality monitoring network that we did as part of a grant with TCQ and EPA under non-sweet pollution grants. So we measure gauge height, we measure specific conductivity, temperature, turbidity, and flow. And again, turbidity is the key indicator of water quality conditions in Onion Creek. So during this period of the grant, when we finally got some flow, we actually had 6 storm events, but one of them we didn't have, we weren't set up to collect the data at that time. So anyway, we go to storm 2, 3, 4, 5. Well, here was a base flow sample. We collected storm 5 and storm 6. And storm 6 was actually a tropical storm named Hermine that I'll show a chart here shortly. But for each of these events, we collected water samples over a period of time with an automated sampler to look at how does the amount of turbidity and other constituents change over each flow event. Let's see, again, this is started in 2009, goes into about a year later into 2010. So here's from that last one, storm number 6, following tropical storm Hermine, and we see that at the Antioch system, the red is gauge height. So we see that that got up to about 15 feet, so pretty high, good flood conditions, but not anything too threatening to neighboring properties. And a couple of pulses going through from rain, and we see how the turbidity kicked up, and in this case, the peak of it was around 1,200 NTUs, and then dropped down another kick, and then eventually dropping down to, very extremely low levels as that water quality improved. And we also have specific conductivity measurements that kind of track varying amounts of the flow and mixing with different waters. But the key thing is, as this gets down, I believe around 50 NTUs is where we have the valve open and let the better quality water enter the cave. Now, the key thing is these numbers that we got from these 5 sample events. And I'd say, let's focus on these red numbers here. Some of these others are just a little background of the different storm events and details that we won't go into right now. But I wanted to show how, as we total up the contaminants, at least the ones we were measuring going into the cave at this time over these 5 storm events, we see for nitrogen from nitrate was 2,436 pounds of nitrogen that didn't go into the cave. And we know that because we took the samples of water going by and we estimated how much water could be going into the cave and calculated over a ton of nitrogen. That's just nitrogen, and include all the other parts that make up, say, fertilizer, if we're to think about fertilizer being dumped in the creek and recharging the aquifer. And then phosphorus, total phosphorus, 295 pounds. And then total suspended solids, basically all the sediment and junk that's washing downstream. So out of those 5 storm events, we had 190,480 pounds of sediment that didn't go into the aquifer. That's equivalent to about 95 tons of sediment. So if you think about dump trucks of dirt just being dumped in the creek that could be getting into the aquifer, that's what was being prevented. So this shows us that the system is working very well and doing what it was intended to do. This is just a nice quantification of those efforts. And I'll show another slide here shortly that demonstrates how we were getting more water into the aquifer. And you might think, well, we're holding off some water, but yeah, we're holding off the more contaminated water. The key thing is we're not letting this system clog up at any time. So it can recharge at its maximum, other than those brief times for a day or two when we keep the stormwater out. So what we're seeing here is a potentiometric map from numerous wells. You can see these wells in black dots and some with circles where we're doing dye trace studies. And so here's Onion Creek, and this is the edge of the recharge zone. So a lot of recharge is taking place along Onion Creek, not just Antioch, but Antioch is really the largest feature and takes in more water than any other feature that we know about. So you look at this heavy black line, that's the 650-foot contour line of the potentiometric surface, indicating we have a nice ridge that's developed along Onion Creek and seems to be more focused on Antioch. And so this extends out in various directions. So we've mapped this out pretty carefully and seeing that there's a good mound that builds up of water as we go through, a very wet time of a lot of recharge taking place. So as we get into drier conditions, this mound will help feed water into Barton Springs. So at some point the mound dissipates and then we have very dry conditions. And, at the surface, the water table's dropped a lot and spring flow at Barton Springs is decreasing significantly. But we feel like this is actually helping, at least at those times of moderate drought, that helping to keep water in the aquifer. Okay, so next I want to talk a little bit about how we are monitoring the aquifer and how we're monitoring some of this flow going into Antioch Cave. And so the Barton Springs district has been involved in the study of these aquifers and including the Trinity Aquifer underlying the Edwards using multiport wells. And this is a technology that we use West Bay out of Canada, but there's also a Waterloo system also out of Canada and several other systems used to measure discrete intervals within an aquifer. This system, West Bay system, works particularly good for us because it can go to extensive depths. We had, I think, the Antioch well about 1,175 feet deep with about 14 zones in which we were measuring various aquifer properties. On the right, you can sort of see, number one here is a packer that seals off the annular space in a borehole. Number two is just a coupling that connects. Well, I'll say no. This is actually number two is the actual port where we actually take water samples or measure pressures in the aquifer. And number three is called a pumping port. We open a small screen so that we can do slug testing. So we can get all the basic aquifer parameters out of these systems. So the idea of multiport wells is we think about, well, we know that some things are complicated in the subsurface. Sometimes we might have, one aquifer and a confining unit and then another aquifer or permeable zones. So we might want to know all about those. So we might put in three nested wells, real close to each other. But you're also drilling 3 holes, so there's a considerable expense for that, even though it's pretty simple in its overall configuration. But with a multiport well, we can actually go in and put in a zone, say one zone in the upper part, one in the middle part, and say the confining in a zone below. But as long as we're putting in more zones, putting in zones like this, we might as well do more. We can put in any given number of zones that we want. So in this case, we're actually having like 6 zones, but one of them might just be the uppermost zone. It might not have water there, and 2 more zones in the confining unit, and then down deeper, we'd have 2 or even 3 zones that we're monitoring these units in. So the district has put together a number of these. This is just showing locations of 3 of them, and then Antioch Cave in particular. We were just talking about that. To the west is Ruby Ranch, and to the east is at Texas Disposal System designed to monitor the saline Edwards zone. And we look at this in cross-section. We see here, so the Edwards is in gray, and of course, all the faulting with the Balcones fault zone. So we have, here's the Antioch system that goes through the confining units above the Edwards, and then the Edwards, and then we get down to the Glen Rose and actually TDs and the Cow Creek Formation. And just to the west at Ruby Ranch, we also have a system that we put in also down to the Cow Creek, but not as deep, because of the faulting going through there. And of course, going further east, and we get to the saline zone, and that's where we have this that other well that we put in, and going down into through the saline Edwards and a little bit into the uppermost Trinity. Okay, well, here's just one of the rig drilling our well at Antioch. So as we drill the well and log it, we need to figure out where do we want to put these zones. And so we work carefully with, looking at the logs, thinking about what do we know about the hydrogeology and the hydrogeologic units, and start designing where we want to put in packers that will seal off distinct hydrologic units. So here we're laying out all this PVC pipe in white, and the blue parts are the packers that are used to separate each zone. And there's a lot of other components to this too, but I'll mention those just briefly here as we get into some of the particulars of the West Bay Multiport system. So on the left is the rig is, after drilling the well, we install the PVC pipe, and here's a packer being lowered down. It's on a 5-foot PVC pipe, but the packer itself is about 3 feet long. And this is inflated with water to seal off the annular space from one zone to the other. So this is going into a borehole that's basically just a bare wall borehole, although in most cases we use a guide tube to help get that pipe in there, and then we pull that out. So we have this plastic urethane is inflated, pushes up against the borehole and seals well, so we can have higher or lower pressures above and below. And on the right, we just see a couple of these couplings of the PVC being fitted together. A couple more pictures showing as we're getting this set up for actually inflating the packers. There's a system here where we inject water, measure the amount of flow going in, measure the pressures, make sure we get enough water going in, enough pressure in those packers so we're certain that they're seated properly and they will seal off any pressure differentials from above and below. And here we are actually taking some measurements as we're lowering our measurement and sampling tool down one of our multi-port wells. Here's a close-up of that tool that I mentioned. This is the sampling and pressure measuring device. So basically what we have to do is line up this little gasket here and this little hole. We have to line that up with a valve at various depths in the borehole, and they have to be lined up exactly, which is partly what this little blue device is here that will connect in a certain spot as we lower it down, and then we know we're in the right orientation and depth for this matchup to occur. And then this device is pressed against the side, opens the other valve, and then we have water can flow from the outside to the inside. And at that point, we're measuring the pressure in the aquifer itself. And if we open another valve, we can let water flow in and fill up some sample bottles that will be hanging below this. So a very unique system, but very good at getting water quality, water samples out, getting pressure measurements, even temperature. And as I mentioned, we can also do slug testing with the other types of devices that are installed. So now just to show some of the results of that, and we'll look first on the right here with our Antioch well. Then this went down to, actually Antioch was 1,375 feet deep with a total of 21 zones. So what we're measuring here is pressures, or converted to feet above mean sea level. And I should mention here, we see above the Walnut formations, all the different units of the Edwards. Below that, upper member of the Glen Rose, lower member of the Glen Rose, and the Hensel, Cow Creek, and ultimately the Hamlet Shale, which is a confining unit beneath all of this. But what we're seeing is there's significant confining units, especially associated with the upper member of the Glen Rose and to some extent the lower member of the Glen Rose. So this is not how one normally thinks about and looks at water levels, but if think about Okay, this blue one was done in September of 2010 and at 630 feet of depth. And as we got into drought, it went deeper and deeper as we go to the green, the orange, and then the red. That was in May of 2011. So we see here, there was a good 40, 50 feet of head change throughout the Edwards units. They all responded pretty much the same as we go from wet times to dry times. Again, this is going from forward in time in this case. But now as we look at in the Trinity, we see that there's very little change, and especially this zone number 10. There's very little change in heads there, if any. As we go deeper and deeper, slight changes. Finally, we get down into the lowermost Lower Glen Rose, and hence on the Cow Creek, and seeing some change, but still nothing like the Edwards we're seeing. So basically, it's telling us there's no hydraulic connection here, whatever that we can see, just because of the pressure changes. But we're also seeing very significant differences in TDS. So we can go through very good Edwards, very low TDS, very high TDS. These are largely calcium magnesium sulfate waters. Then we get back into calcium bicarbonate waters at depth in basically the middle Trinity Aquifer. So this told us that we're dealing with two distinct aquifers, and even then you can divide it into sub-aquifers. But as we look across and over the Ruby Ranch that was nearby, see kind of a similar pattern, but our confining unit is not as thick. The lower, we think because of a Rudis reef in zone number 7, we're actually getting more water moving through the system, and therefore we're not getting the same high TDS values. It might also involve the distribution of some of the evaporite minerals that are causing some of these low permeability and high TDS values. And here's another view. This is hydrographs, maybe a little more familiar, going from back in time to forward in time, going to the right. But we have multiple zones that we're measuring here, 21 in this case. But we can see two distinct packages. This one zone, one set of zones here that is changing a lot. So we're basically looking at the Edwards here. And here we have the Trinity that doesn't change near as much. And we see how the Edwards is higher, then lower, then higher again, as we went through this period of time from 2010 up till 2012. And we're missing a little bit of data in here. We have some of these intermediate zones, but they're basically showing how they're also intermediate in pressure and changes over time. And just a quick view of what's down the well. So this is why we see some evidence of that low permeability. Is basically we have evaporites, probably gypsum, it could be anhydrite, plugging up pretty much any porosity here at depth of 1,045, 47. Then as we got deeper into the lower Glen Rose, lowermost Glen Rose, 1,298 feet. This is looking to the sides, some fractures and basically conduits. And at 1,345 feet in the Cow Creek, we see some fractures with a little bit of dissolution there, showing that we have some decent flow of water moving through basically karstified, dissolved limestone to open up these pathways. And looking again at that same figure, showed it blown up a little bit more here and showing some more data, but again, showing that considerable spread in the Edwards and almost no spread in some of this middle Trinity, and then moderate amount of spread of heads over time in the middle Trinity. So that's pretty much what I have, and I guess a little later we'll take a break, and I'll be glad to answer questions at that time. So thank you for your attention.